Good morning. Welcome to the fourth lecture on engine introduction to engine optimization. And in the last class, we have tried to cover certain classification of engineering optimization problems. So, as we know, these problems are classified based on the constraint, based on nature of design variables, based on physical structure of problem. Up to this we have discussed yesterday, and we will continue our discussion on based problem based on classification on physical structure of problem. Then I will try to cover other remaining classification, that is remain nature of equations, deterministic nature, permissible value of design variable, separability of function, and number of objective function. I will cover in today's lecture itself, and I will take up problems corresponding to these classification in later classes. Okay, so this much topic I will try to cover today. So this we have covered, and we were here. Yes, classification based on physical structure of problem. So under this we have optimal control problem and non-optimal control problem. So optimal control problems are those mathematical programming problems in which there are number of stages, and where each stage is evolving from your proceeding stage. Okay, so we took one example. I will read again this example. This is a problem related to your optimum control problem. Okay, so in optimum control problem, as I told, that your there are number of stages, and each stage is evolving from your proceeding stage. Okay, so let us take one example of this. A rocket is designed to travel a distance of 12 seconds in a vertically uh, uh, in a in a vertically upward direction. The thrust of rocket can be changed only at the distance point located at sorry, it is not 12 second, it is distance 12s. Okay, there is some constant s, and it has been divided in 12 discrete stages. So the first point is at 0 distance, then second point is at distance s, then next point is at distance 2s, fourth point at 3s. Likewise, there are 13 points, and there are 12 segments. We can say segment 1 will be from 0 to s, segment 2 will be from s to 2s, segment 3 will be from 2s to 3s. So this way there are 12 stages or 12 segments. Okay, and in there are other conditions also. If the maximum thrust that can be developed at point I, either in positive or negative direction, is restricted to a value of Fi, formulate the problem of minimizing the total time of travel under the following assumptions. The rocket travel against the gravitational force. Okay, it is quite natural. The mass of rocket reduces in proportional to the distance travel. Okay, so your mass is proportional, mass is reducing in the proportional to the distance travel. Okay, so suppose at the end of segment 1, if the proportionality constant is a certain value k. Okay, so the at the segment of end of segment 1, the mass will be reduced by a value, certain value k into s. Okay, so this we will take up then during the discussion. Okay, then there is third constraint, the air resistance is proportional to the velocity of your rocket. Okay, so there are three conditions. The rocket travels against the gravitational force, the mass of rocket reduces in proportion to the distance traveled, and the air resistance is proportional to the velocity of rocket. Okay, so let us have a look on this figure. Here we can see we have this starting point, which where distance is we have kept it as 0. Okay, at the end of first segment or the first stage, the distance is s, then third 2s. Likewise, these distances are 2, 3, 4, 5, 6 up to 12s. Okay, so if you take up the control points, so how many control points are there? These control points will be 1 plus number of stages. Okay, so there are 12 stages, so the number of control points are 30. Okay, so these control points are starting point 1, 2, 3 and up to 30. Okay, so these are 13 control points, and let us consider that xi is denoting the thrust, Vi is denoting the xi is denoting the thrust at point I. Okay, so here x1, here thrust will be x1, at control point 2 this will be x2, at control point 3 this will be x3, x4, x5, and on your control point 13 your thrust will be x13. Okay, so similarly the velocity at control point at point I, it is denoted by Vi. So the velocities, corresponding velocities will be v1, v2, v3 and up to v13 or v13. Okay, similarly the acceleration is denoted by AI. So M1 and AI. So A1, A2, A3 up to A30. And the mass of the rocket at point I is denoted by Mi. So this mass at starting point will be m1, then at point 2 this will be m2, at point 3 this will be m3. Obviously the mass will be changing, velocity will be changing, the thrust will be changing from control point 2 up to control point 13. Okay, so as per the Newton's second law of motion, we can say net force at any point, the net force on the rocket is equal to mass into acceleration. Force F equal to ma. We already know this in our from 8th class. Okay, so this can be rewritten as the net force on the rocket. How we can calculate thrust, and the thrust is acting against your gravitational force and air resistance. It is acting against your air resistance as well as against your gravitational force. So the net force will be reduced, that is the thrust will be reduced by the value of gravitational force as well as air resistance. Okay, and this may be equal to, this will be equal to F into m into A. Okay, force and net force equal to mass into acceleration. Okay, I hope this much discussion is quite clear. Let us move forward. Let us take any point I. So this thrust, again from this formula, thrust will be xi, and gravitational force will be a mass at this point mi into g. Okay, and here k1 is your constant for calculating your air resistance. So suppose vi is the velocity at control point I, so the air resistance is given by minus k1 into vi. Okay, so at any control point I, the net force will be xi minus mi into g minus k1 vi. This will be equal to mass at that particular control point, that is mi multiplied by acceleration at control point. Okay, so because this we are talking about any control point between ranging from 1 to 30. Okay, so because the mass is reducing at each stage, so we have to also consider the mass reduction factor also. So how this mass will be drawn from your previous stage, or how this mass will be decided based on your proceeding stage. This may be given as mi equal to mi minus 1, that is the mass at preceding stage. This will be subtracted by a certain constant. Okay, so this constant, how we are taking, the mass of rocket reduces in the proportional to the distance travel. Okay, so how much distance this mass will travel from your proceeding stage? This will be, because these segments are of equal distance, that is s. First segment is ending at s, second is ending at 2s, third one is ending as 3s. So in each segment there is a distance difference of s. The distance traveled is s. Okay, so that is why this reduction is mass is taken as k2 into s. So at any control point I, the mass may be given as mi minus 1, that is the mass at the preceding stage, subtracted by the loss of mass from preceding stage to the current stage. Okay, so that is why mi is equal to mi minus 1 minus k2 s. Okay, here k1 and k2 are constant. Okay, and let us rewrite this equation 1. Ai may be given as, if we take ai in one side, this will be xi upon mi. Okay, xi upon ai, mi will be cancelled, so this g will remain. Then k1 v1 upon mi1. So we have rewritten equation number 1 into equation number 3, and we have calculated as ai equal to xi upon mi minus g minus k1 vi upon mi. Okay, I hope it is up to this. There is no doubt. If there is any doubt, you may ask. Otherwise, I will move. Okay, those who have having any doubt, they can ask so that I can move further. Okay, so let us move forward. Yes, somebody is asking. This equation number 2. Okay, so let us see this figure. Your control points M1. Suppose mass at control point 1 is M1. Here is M2 at control point 2. Here is M3. Okay, and at control point 10 it is M10, M11, M12, M13. Okay, and in your problem, what is the second condition? The mass of rocket is reducing in proportional to the distance travel. Okay, so suppose this m1 the mass at control point is m1, and mass at control point 2 is m2. So what will be the difference between these two masses? M1, obviously m1 will be higher and m2 will be lower. Okay, and how can we calculate m2? M2 will be equal to m1 minus certain constant. Okay, that constant we have taken as k2, proportionally constant, multiplied by distance travel. Okay, so this will be m1 minus k2 into s. Okay, this is for calculating mass at stage 2, this control point 2. Okay, because the distance travel is s, and we as soon as we multiply with the proportionality constant, we have taken one proportionality constant k2. So this reduction is in mass from point 1 to 2 is calculated, and it is given by value k2 into distance travel, and distance travel is s. Similarly, in the next segment, are you able to get this reduction in mass from control point 1 to 2? Uh, Yes. So similar thing will be repeated from distance that is control point 2 to 3. Here also distance, how much distance is there? S to 2s. So the distance travel will be again s. The segments are of equal distance. Okay. So again in this segment, the reduction in mass will be k2 into distance travel. What is the distance travel? That is s. So this will be k2 s, and the mass at control point 3 may be given as m3 equal to m2 minus k2 into s. So we have written this equation 3 in general form, that the control point, that is a mass at any control point, may be given as mass at preceding stage divided by subtracted by k2 into k2, where k2 is your proportionality constant for mass reduction, so, multiplied by distance travel. Okay, since the distance travel in each stage is same, so we have taken it as s. This may also vary. Okay, in other example or in some problems, this distance may not be equal. Okay, but for simplicity, we have taken this distance as equal for each segment. Okay, so that is why this mi is given as mi minus 1 minus k2 into s. Okay, I hope this equation 2 is clear. Uh, this from equation 1 we have derived equation number 3. Only we are computing the value of ai, that is acceleration at any control point I. Okay. Any doubt up to this point? Okay, I hope there should be no confusion. Yes, thank you. So let us consider a few things more. If Ti denotes the time taken by the rocket to travel from control point I to control point I plus 1. Okay. So what is Ti? Ti is not the total time. Ti is the time which the rocket is taking from for traveling from control point I to I1. Okay, so try to understand from this figure. The time traveled, time taken by the rocket for traveling from control point 1 to 2 will be given as T1. Okay. Similarly, the time taken by the control point, time taken by the rocket to travel from control point 2 to 3 will be denoted as T2. Okay. So this, let us take for generalized form, we are denoting it as Ti. Okay. So obviously this we this ti is the time from one control point to and time taken between two control points, that is from I to I plus 1. Okay, so what we do, if we apply second law of motion, sorry, uh, we know s equal to ut plus half at square. This formula we already studied in our elementary classes. So we apply this formula in these two segments. What your u will be vi, and time taken will be ti. So this will be s distance traveled s equal to vi ti plus half acceleration ai half ti square. Okay, so uh, here what we can do, we have we know vi, we know ti, we know we have calculated AI in equation number 3. What is AI? AI equal to xi upon mi minus g minus k1 vi upon mi. So if we simply put this value in your equation, we will get equation number 4. Okay, so we have taken all the values in one side and equated it to equal to 0, and we have put the value of AI. Simply the value of AI has been put in this formula. Okay, so I hope this is quite clear. 1 upon 2, we have put AI, value of AI. This is xi upon mi minus g minus k1 vi upon mi multiplied by ti square plus ti vi minus s equals to 0. Okay, so if you try to see the nature of this equation number 4, if it is clear to all of you, this what we are supposed to calculate, we are supposed to calculate the value of ti, that is the time taken between from point I to I plus 1. Okay, so what is the nature uh, of this equation? We can see this equation is of quadratic nature, quadratic function. Ax square plus bx plus c equal to 0. You might have studies that how we get the values of x if we are having a quadratic function, that is ax square plus bx plus c equal to 0. We calculate the value of x equal to minus b plus minus root of b square minus 4ac upon 2a. This we have studies in might be in 9th or 10th. You might have studied how to calculate the roots of a quadratic function. Okay, so the similar things we will apply on equation number 4, and we will get two values of ti. Okay, these values may be given as ti equal to minus b is replaced by vi, so b plus minus square root of p square minus 4ac. So this will this minus will be plus, so this is 2 as xi upon mi minus g minus k1 vi upon mi upon 2as. So this upon 2a, sorry, so upon 2a, because here half is already there, so if we multiply it by 2, only this value will remain, xi upon mi minus g minus k1 vi upon mi. Okay, so using this equation number 4, we have calculated the distance traveled from one control point to another, time taken by the rocket from one control point to the another control point. Okay, so for t1, this will be v1 plus minus v1 plus 2s x1 upon m1 minus g. Okay, likewise we can calculate the time traveled for any segment of your rocket. Okay, so in this equation, let us try to simplify it. Okay, so suppose at control point 1 the velocity is v1, and at control point velocity is v2. So we know that v equal to u plus at. Okay, so here v will be v2 equal to v1 plus a1 t1. So since we have calculated ti, we can calculate the change the velocity at control point I plus 1. So suppose vi is the velocity at control point I, and vi plus 1 is the velocity at control point I plus 1. So this may be given as Vi plus 1 is equal to Vi plus acceleration into time from taken by the rocket from control point uh, I to I plus 1. So this is given by T. Okay. So any confusion up to this point, any doubt in any equation, so that the problem did not become complex. Any doubt? Okay. So Vi plus 1 equal to Vi plus Ai Ti. Okay. So if we put the value uh, sorry, equation number 6, in equation number 6 what we are putting the value of Ai as well as uh, Ti. Okay, so if we put the value of Ai and Ti into equation number 6, that is these values from where we are putting from Ai we are taking from equation number 3 and Ti we are taking from equation number 5, and if we simplify this equation this will end up Vi equal to square root of V square plus 2s xi upon mi uh, uh, xi upon mi minus c minus k1 v1 upon mi. Okay, so up to equation number 7 I hope everything is clear to each one of you. Okay, so since this rocket was traveling from your control point 1 to starting from control point 1 and it was ending or stopping at control point 13. Okay, so at what will be the velocity at control point 1 v1? This initial velocity will be 0 as well as your end velocity at, that is the velocity at control point 13, it will also be 0. Okay, so v1 equal to v13 is equal to 0. Okay, so any doubt up to this point? If there is no doubt, so let us move forward. Okay, so now we have calculated the unknown. We can now we are able to calculate the values of Ti, Vi, Ai for each stages. So we can formulate this problem. What was our objective function? So we are calculating the thrust at control point x1, x2. Sorry, control point. We are calculating the thrust at for segment x1, x2, x3 up to x12. Okay, and what is the time taken? That time taken is given by for these 12 segments. The time taken is given by from 1 to 2 is t1, from 2 to 3 is t2, and from 3 to 4 is t3. Okay, so there are 12 segments and there are 12 segment of time travel. Okay, so so what, in order to get the total time, what we have to do, we have to do the summation of all the times. Okay, so t1 plus t2 plus t3 up to t12. Okay, so here the time travel from 1 to 2 is t1, 2 to 3 is t2, 3 to 4 is t3, 4 to 5 T5, 10 to 11 T10, 11 to uh, just a second. Okay, from 12 to 13 T12. Okay, so this time if we want to calculate the total time of travel will be T1 plus T2 plus T3 plus T10, 11, 12. Okay, so up to 12 there will be 12 segments of time that uh, we have to do summation in order to calculate the total time taken by the rocket. Okay, and see the issue. What is the issue in this problem? Formulate the problem for minimizing the total time of travel. Okay, so what we have to do? We have to do summation, and the problem will be the minimization of this your total time. That is the summation of T1 to T12. Okay, so let us come here. So we have thrust at x1, x2 up to x12, and the problem of your optimization problem is optimum control problem, because each stage each stage was evolving from your previous stage. Okay, so here fx will be equal to summation of, that is the objective function, fx will be equal to of I varying from 1 to 12 summation of ti. Okay, so this ti, this value may be given as minus vi. Okay, so here also you can see one thing, why this only positive sign has been taken. So I will tell you, just see this value of ti is minus vi plus a square root of v square plus 2s xi upon mi. So this value has been substituted from equation number 5. Okay, so here one thing is interesting to note, that since your time ti is time taken by rocket from one control point to the next control point will be positive value, the time cannot be negative value, and in this expression we can see vi is negative value, and the plus minus sign is there, and there is some another value. Okay, so which sign will be accepted? The value with positive sign will be taken as, so that the time is calculated as positive, because time cannot be negative. If we take both the negative values, the time will this numerical value will come negative. Okay, so, but in practical life, we know the time travel from one control point to another control point cannot be in negative. Okay, so this positive sign will be accepted, and the negative value will be rejected from equation number 5. Okay, so that is why this positive value has been taken. Okay, so this value of ti will be minus vi plus square root of v square plus 2s multiplied by xi upon mi minus c minus k1 vi upon mi upon same value. Okay, so here this is our object. Now we are actually able to formulate our given problem into your mathematical problem. Okay, so this is our objective function, and what are the constraints? Constraints are mi1 plus mi plus 1 is equal to mi minus k2s, where I is ranging from 1 to 12. Vi plus 1 is this velocity of at any control point, that is given by Vi plus 1 equal to velocity square root of velocity at square of velocity at proceeding stage multiplied by 2s thrust at proceeding stage divided by mass at proceeding stage minus c minus k1 into velocity at proceeding stage divided by mass at proceeding stage. Okay, or and here I again will be ranging from I to 12, 1 to 12. Okay, a thrust will be always less than equal to Fi. Okay, and here also I will be ranging from I to 12. The necessary condition is V1 equal to 0 as well as V13 equal to 0. Okay, so in this total discussion, we are only till now we are only able to formulate the problem, how we have to proceed for this optimum control type problem. Okay, so any doubt up to this discussion, students? Okay, so I suppose there is no doubt. Okay, so after the formulation of problem, you can solve these problems by using optimization techniques, maybe using by graphical method or maybe any other method. But the formulation of problem into mathematical expression is important. So it takes quite time, and understanding is required about the nature of your problem, what kind of problem is there, and what are the constraints that should be considered while formulating the problem. Okay, so uh, we were discussing about the classification based on the physical structure of problems. Okay, so we have discussed optimum control problem. What may be what problems may be called as optimal control problems. There may be other problems in which the each stage or there if there are stages, then stage is not evolving from the preceding stage. Those problems may be called as non-optimal control problem. Okay, so now what I will do, if we have 15 minutes more, so what I will do, I will quickly go through the remaining classification so that I can cover the classification portion quickly, and later on in coming lecture I will take the problems related to this classification. Okay, so let me quickly finish the classification, and then we will take up the problems based on these classification, and maybe tomorrow onward. Okay, so I will finish this classification topic. Okay, so moving forward, you have next type of classification of engine optimization problems, that is classification based on the nature of equation involved. Okay, so the based on the nature of expression for objective function, constraint optimization problems can be classified as linear, non-linear, geometric, or quadratic programming problem. Okay, so as the name indicates, the objective function or the constraint uh, will be the linear function of your design variable. Okay, so these type of problem will be called as linear programming problem. If the objective function and constraint are non-linear, then these problem will be called as non-linear programming problems. Okay, so we will take up examples of these problems in coming lecture. Then we have another type of class of problem, that is geometric programming problem. In this, the objective function and constraint are expressed as the polynomials. Okay, so okay, then we have quadratic. I will finish quickly, and these classification will be retouched during the whenever we will take questions in coming time. So then we have quadratic problems. So in quadratic programming problem, what is quadratic objective function, and there are quadratic objective function and linear constraint. Okay, then we have another type of classification, that is classification based on the permissible values of control variable. Under this classification, problems can be classified as integer and real value programming problems. Okay, so integer programming problems are if some or all the design variables of an optimization problem are restricted to take only integer or discrete values, the problem is called as integer programming problem. Okay, so here only integer values is taken for the design variable. In real values programming problem, the values may be even in decimal. Okay, so or up to 6.7 point of decimal. So in real values programming problem, the the real values are taken to minimize or maximize. Let us take one example. Let's suppose uh, we are maximizing certain production. We are maximizing production of certain product. Say production of chair, production of tables. So production of tables, when we are optimizing the production of tables, what will happen? Your these production of tables cannot be in fraction, like 4.5. Either it will be 4 or it will be 5. It cannot be 5.1. This will be either 5 or either 6. Okay, so this way the real values are taken, sorry, integer values are taken based on the design constraint and the objective function involved. Okay, so but if we are maximizing profit, it can be 5.25, it can be 5.2 crore, 5.5 crore. This can be in real values. Okay, there is no need, there is no constraint that the value needs to be integer value. Okay, so this type of problem we will discuss. Then we have next type of classification, that is the classification based on deterministic nature of the variable. So under this classification, optimization problem can be classified as deterministic and stochastic programming problem. So what are the deterministic programming problem? So as the name indicate deterministic, that something that can be determined. Okay, so what can be determined? The design variables are deterministic in nature. Okay, these can be distinguishedly determined. Okay, but there may be cases where when we are not able to determine the values of design variable, we have probability or the nature of design variable is probabilistic, that is non-deterministic in nature. Those type of problems are called as stochastic programming problems. Okay, we will take up these problems based on this classification also. Then we have next type of classification, that is based on the separability of the function. Okay, so under this we have separable programming problem and non-separable programming problem. Oh, okay. So in separable programming problem, the objective function and constraint are separable. We will discuss how these are while taking problems, that how this function and constant are separable and how the problem are called as non-separable programming problem. Then uh, we have last type. This is the last under this topic, that is a classification of optimization problem, that is classification based on the number of objective function. Okay, so under this classification we have in previous lecture we were discussing that there might be single objective function, and there might be multiple objective functions also. Okay, so if there is only one objective function, that is a single objective function is there, then we may call it as single objective programming problem. Okay, and if there are more than objective function, then the problem is called as multi-objective programming problem. So this I will end up today here. Okay, so if there are any doubts on the discussion till now, we can take up. Otherwise, we will move forward in tomorrow on the problems based on these classification. We will start taking problems from tomorrow onward. Okay, any doubts till now?